Hello everyone. Welcome to this session on wireless design with MATLAB. My name is Mandar and I'm applications engineer with the MathWorks. Now those attending this session, I'm sure you will agree that in the past few years, we have changed the way we communicate with each other. We have already thrown away those old mobile phones and replaced them with something looking like this, more sophisticated, which offers us more features in a way that we can stream music, we can stream videos live. We can take photographs whenever we want, where this particular feature was not available through the old phones. The reason is the technology. We have moved away from the old CDMA phones or 2G and 3G, and now I'm sure that in most parts of the world, 4G revolution has happened. 4G is a technology which has been widely used on the mobile phones nowadays. And the amount of data which we share nowadays is also huge. And therefore, we are already living in the era of Internet of Things, where things are trying to talk to us, trying to talk to each other as well, communicating something. And while this communication happens, we want to ensure that the level of communication is top notch. The channel is nice. In fact, most of the companies around the world are now adopting LTE as the medium of communication for Internet of Things. Now, with these technologies, we are sure that in the era of, as we are living in the era of 4G, there are lots and lots of releases, lots and lots of advancements which have happened in the 4G space as well. New features are coming in, and we are moving towards 5G. Also, in the WLAN space, we started with 82.11a back in 90s and now move towards 82.11ac as a WLAN standard. We have already adopted those. New standards are being proposed, something like 82.11p for car-to-car communication as well. And with this advancements in the communication technology, which is continuing, there are lots of new things are being proposed. Things like massive MIMO, headnets, small cells, new modulation techniques. And the only reason for those is to enable the user with high data rates, to ensure that there is reliable service everywhere, to see that there is high connection density and efficient use of spectrum. So that's how the air interface technology has evolved or is continuing to evolve. I'm sure while this is true, before we get to see the technology working or before we try to experience this technology on our mobile phones, there's lots and lots of efforts being put in. And in the case of for a wireless design engineer, there'll be a lot of questions in their mind. Questions like, before I want to see this happen, if I want to implement this on the hardware, I would like to simulate the communication system so that I can check the effects of various parameters, interference, beamforming, transmitter power, um, interferer power, and so on and so forth. Can we simulate this? We talked about different technologies, 4G, 5G. Are there any channel models which I could use? I mean, these channel models, I would like to use some of these channel models in my communication system. Is there anything to use it readily? And while we are talking about the digital communication system, some of us may want to design antennas, visualize their parameters, test their performance on a specific band, such as the Wi-Fi band. Is there something which we could use to design the antennas as well? And once, as we are progressing through these three steps, the last steps eventually, if everything works properly, you would like to test this on a hardware. So can MathWorks help you to get all these things right? So why not let's make those things our agenda and enter the discussion. Okay, so let's start with the first one. How could you simulate your communication system and see the effect of various parameters? Now, before we jump into this, let me briefly introduce you to the digital communication system environment. It consists of a transmitter, In the transmitter, there's lots of things happening. Say, for example, if you're speaking, if you're transmitting a voice signal, that voice signal then converts to bits. There are lots of other things like channel coding, modulation. If you're transmitting with multiple antennas, that serial stream gets converted to a parallel stream, such that it is now transmitted on the antennas. OFDM modulation is frequently used for most of these wireless communication technologies. Once your signal has been modulated, it's ready to transmit, it enters the wireless medium, which is air. It's a very volatile medium, and therefore lots of impairments, lots of things happen in the channel as well. Things like large scale fading, small scale fading, multipart, Doppler effect, interference from other systems, noise, and so on. And by the time while it's in the channel, it gets sufficiently, the original signal gets sufficiently corrupted. And this corrupted signal then goes towards this receiver, to its intended or some other receiver. And in the receiver, we need to correct these impairments, correct the corrupted signal nicely. And therefore, whatever things happen at the transmitter, the opposite things happen at the receiver. So OFDM modulation becomes OFDM demodulation. We try to estimate the channel, then come up with the equalizer, demodulate it, and finally, after channel decoding, try to recover the output bits. Sometimes these output bits could be same as the input bits, but most of the times they are error. And we not need to make some sense of the signal which we have recovered. So that is typically how the digital communication system work. So something like this, a base station over here is trying to convey some information to its intended receiver. While this is happening, there's also some interfering base station from another cell which is trying to give some other signals, which is the interference. There could be things like multipath fading and other things. We need to properly decode, properly recover the signal which this particular mobile is supposed to listen. And while we're talking about all these things in the transmitter, receiver, channel, there are a number of challenges. Challenges like how do I play with these fading channels? How do I come up with these interfering signal? Can I do some things like beamforming, beam steering? Can I design these antenna arrays? How do I estimate the channel? What kind of equalizers are possible? Can I design my own equalizers? And things like that. So these are some of the challenges which we would like to address. Okay, so let's see an example of a simulation. How can you simulate a communication environment? And over here, I'm going to show you an example of a telemetry. In this telemetry example, a GUI will pop up or an app will pop up. And through this app, you're able to tune some of the parameters like the transmitter power, mobile range, modulation, interferer range, interferer power, and so on and so forth. So what is happening in this demo is there is an unmanned vehicle which is surveying a geographical region. While surveying this geographical region, it is taking some videos, and these videos are then getting sent to a base station. From the base station, the video signal gets routed to its intended receiver, which is shown in green over here. Now, because it's the medium of communication is air, there's lots of other things. There's an interferer as well who is trying to corrupt the signal. So this is the kind of an interferer which is corrupting the signal, and it's adding some other signals like the crosstalk. So we need to check what happens if the transmitter power is high, what happens if the transmitter power is low. Combine that with the interferer power. How do I get how better the communication is? Am I able to receive the same video signal as the way it was transmitted? Is there going to be some loss? What happens if I change the beam angle, steer the beam in some other location than its intended mobile? Will there be any change in the communication system? So let's have a look. How can MATLAB help you? So I'm into MATLAB and I'm trying to fire up that telemetry demonstration. So I'm just running this particular file, Z run me first, and I'm going to start this demonstration of the full transceiver used in telemetry. So let's have a look if you are able to achieve what we said. Can we see the change in the signal by adjusting the parameters? So some messages get popped up. Calculate antenna radiation pattern depending on the number of antennas transmit and receive. Is trying to design these antennas and use them. So over here we have MATLAB has given us that app which we can tune. It has given us the transmitter power, receiver power, and so on. That's the constellation diagram. Okay. So the video you see in color, that's the video which that unmanned vehicle is transmitting. And what you see in the black and white is the signal upon reception. So the transmitted video is changed to bits, and these are the different bits in these are quadrature amplitude modulated QAM signals. Ideally, these points need to be resting at one point, typically in the center, but they are not. They are scattered. They are just moving all over around. So this is what the received signal looks like. So ideally, I would like to see these points in the center. So because of the noise, because of the signal, um, uh, different kinds of noise or the impairment of the channel, the received signal is quite corrupted. And you could see some artifacts which you could see, you can view them at the received signal, some things like these. So that's the blue circle is what the interferer is. The red dot with a green border is the intended receiver. And at the center over here is a base station. So what happens if I lower the transmitter power? So you could see as you lower the transmitter power, there's lots and lots of errors. The constellation is errored. The received constellation is errored. And you can see the change is present. If you see the transmitted signal, you can see the equalized signal there. This is spectra, so there are some changes happening in the equalized signal as well. Okay, so there is a limit. So maybe let's bring it back, something like that. What happens if I lower the interferer power of this particular mobile? If I lower it, okay, the constellation gets better and better. Okay, so that's the ideal. That's what we wanted. That's actually something like this which we will love. But of course, it is not possible to have an ideal communication environment in practice. All right. And also, if you were to make your transmitter power sufficiently high, that means it will prove more and more expensive. Okay, so let's do something realistic. Okay. So what happens if if this particular internet receiver moves outside that range? So whatever is happening over here, that pink globe is the beam steer. The base station is steering the signal in the direction of the internet receiver. So what happens if this particular receiver moves outside that zone? So let's see the mobile, let's change the mobile angle to say 23 degrees. All right. Even without touching the transmitter power and the receiver power, if the mobile departs its zone, safe zone, then the signal is significantly errored. You can't get anything out of it. It's all noise. That's because the base station is focusing all its energy in a particular direction. To correct that, what you will need to do is need to direct that beam in some specific angle where this particular mobile is. Okay. So if it is 52 degrees, let's change this steering angle to 53 and I hit enter. So I'm changing the beam steering. The beam is now steered at an angle of 53 degrees and I'm able to get that signal back. I can even change the transmitter power to see if everything is back to normal. Okay, so this is something which you would like to do, which a typical wireless design engineer would like to do. You'll be given the codes and you can continue to explore the codes, and there's lots of other things which could be done in this particular demonstration. So let's go back to the slides. So what we did over here, it was a classic case of MIMO OFDM communication environment. The reason because lots of technology, lots of wireless communication technology make use of OFDM or a variation of it. Okay, now how is this possible? Now communication system toolbox has got lots of functionalities which are catered for these modulation, demodulation techniques, for encoding and decoding techniques like convolution encoder, Viterbi decoder. There's lots of functionalities for interleaving, lots of functionalities for creating the channel, different kinds of channels, Rayleigh, Rician, adding thermal noise to your data, and so on and so forth. And there are also functionalities if you want to design the equalizer. Now, one question which will come into your mind is, all right, there are lots of functionalities, but these functionalities don't look normal. They have something like com dot general QAM demodulator, com dot turbo encoder, com dot block interleaver, and so on and so forth. So what is com dot? Now, what we have over here is our a collection of system objects. Now, because these system objects rest in the communication system toolbox, that's the reason why you have com dot general QAM demodulator. So it's a general QAM demodulator system object. Now, the question would be, if there's a system object, what is a system object and how can you play with a system object? How could you apply system objects to your data? So let's have an example of that as well. Okay, so I'm going back to MATLAB and over here I'm going to open an M file. Now this particular M file will introduce you the world of system objects. Now over here I'm just trying to do simple things. I am creating some bits, generating some random bits, modulating the signal, adding noise, and I'm visualizing the noisy constellation. So over here in the first three lines is just some setting up some values for those variables. And on line number 12, 13, 14, that's where I'm creating or initializing the system objects. If you want to create a QPSK modulator system object, that's what you will say, com.qpsk modulator. Over here, I'm creating a system object for the AWGN channel. And then I've got another system object for the constellation diagram. What we see over here, the properties which are associated with the system object. There are lots of such properties which you can set. Now, once you have initialized a system object, how could you make use of it? So let's have a look. So once I have initialized a system object, I have started a for loop. I'm creating some random bits to transmit. So you are my random bits. And then if you want to modulate your bits, all you're doing is starting the step function. So step modulator u. That's your modulator. So what you get out of it is a modulated signal. Once you get your modulated signal out, you want to go add some noise to it. So again, there's a step function adding noise to the modulated signal. And once this is what is the variable receive signal, you want to then introduce them, or you want to put these noisy signal on the constellation diagram. So therefore, I'm again using a step function. How this works? So let me have a look. Let me run this. So I've created these system objects. So get system objects for modulator and so on. That's a system object. That's another system object. That's another system object, and so on. And once you have done this, you are just doing some stream processing for 500 iterations. Okay. So that's how you'll do. So all we're doing over here is creating these system objects and stepping it. And once you're done with your job, just release those objects. All right, so that's what it is. That's how the communication system, which I showed you previously, has been designed. So making use of all these system objects, we have designed a range of communication systems. All right, and all these systems you'll find in the previous version over here. So you can have a look at the SISO transceiver in the same way, single input, single output, no beamforming. So I'm just starting that up. So I got the transmitted and the received signal. I've got the QAM constellation, and that's the chart. So SISO, no beamforming, so the antenna is radiating in all directions. What happens if you increase the transmitter power? What happens if you decrease the interferer power? It gets better and better. What happens if you change the modulation order? So if I want to go for a 4 QAM and so on and so forth, you can do that. Okay. So you can also have a look at how the code has been constructed. So we can have a look at the MATLAB code. And in that MATLAB code, you'll see that everywhere we are first initializing the system objects for scrambler, descrambler, convolutional encoder, Viterbi decoder, and what you're doing next is just stepping on it. Okay. So creating the bits, modulating it, creating some path losses, applying those path losses and the noise, and doing the detection steps over here. So in communication system toolbox, all we have is number of toolboxes and some other functions, and these number of system objects and some other functions. And these system objects, you can activate these system objects by just using the step function. Okay. So you'll get these codes. These codes could be downloadable, and then once you're able to download, you can explore what the different versions are and how they're constructed. All the idea remains the same: construct a system object and use the step function. Okay. All right. So that's the first one. Let's go to the second part of our agenda, and the second one is: are there any ready-to-use channel models? Well, um, let's have a look. So with the comms toolbox, there are lots of channel models which you could use. So what we'll do is we'll go to the documentation center. Let me close this and let me clear everything off, and let's start the documentation center. So in the documentation center, let's navigate ourselves to the communication systems toolbox, and inside the communication systems toolbox, you will find something for channel modeling. So there are lots of blocks and lots of system objects for channel modeling as well. Okay. So you can construct a AWGN channel, LTE MIMO channel, or simple MIMO channel. You can have a Riley or a Ryshan channel, and so on. So there are lots of system objects which are just catered towards that. All right. So this is some standard ones. So what about for 802.11g platforms? So 802.11g, AC, and so on. So let's have a look at that as well. So let's go back to the documentation center, and now we will be entering into the WLAN system toolbox space. So WLAN system toolbox, propagation channels, And also over here, there are system objects for if you want to construct 82.11 AC, 82.11 N, there are system objects catered for just that. In addition, it gives us a function std_chan. std_chan is a function which is a part of a communication system toolbox. So std_chan is a part of comms system toolbox. Now, in association with that, you will get used to get access to lots of channel models. Rural, urban, hilly, you know, and then you can go to indoor office, indoor office, channel A, channel B, satellite channels, channels at medium altitude, low or high altitude, residential channels, hyperland. Over here, you can also use chan function to construct 82.11 A, B, G channels and so on and so forth. And over here, you can also see an example of how to construct a channel for 82.11G. So with the in a so in WLAN system toolbox in association with communication systems toolbox will give you access to lots and lots of channel models which you can readily use. And in fact, we are continuing to update these toolboxes or whatever toolboxes we have. We continue to update at most at every release. So one of these updates for WLAN System Toolbox was the addition of 82.11p and 82.11j channel models as well. Okay, right. Having seen the different channel models which are available with the WLAN System Toolbox and the Communication System Toolbox combined, let's move on to the next part of our agenda is how to design antennas, visualize their parameters, and test their performance on some band, say a Wi-Fi band. Now, so for this purpose, we're having two products, the Antenna Toolbox and the Phased Array System Toolbox, where you can design, analyze, and visualize the antenna elements. You can compute the port properties such as the impedance, surface properties, um, check the near field and the far field radiation pattern. You can also integrate the antennas and arrays of the wireless systems and use impedance analysis to design some matching networks. So with these two toolboxes combined, let's see what things we have. Now, the great thing which we have over here is the sensor array analyzer app. And say, for example, if you want to design a microphone array or a sensor array, you've got something called as a sensor array analyzer app. So let's fire that up. Okay, so here is that app, the sensor array analyzer. You can select the geometry which you want to take into account. You can also design your own custom antenna if you wish to. You can also say the number of elements, the frequencies, but for this particular case, I'll just keep it as default and I'll say apply. You can also view the directivity pattern in 2D or 3D and um, lots of other things can be done. So it's calculating the response and soon you should be able to see the directivity pattern. You can rotate it and also if you want you can see the 2D directivity if required. And the good thing about this app is just like the some other ones which we have seen previously, this particular app can also generate the code. So let's have a look how to get the code. So over here you can have an option under file menu to generate the MATLAB code. So and once the MATLAB code has been put up, you'll see that it has done the settings. So whatever parameters you set in the app, they have been translated, they have been migrated onto this code. And things like face dot conformal array, you get to see some things like this face dot cosine antenna element. Now again, these are system objects now which are part of the phased array system toolbox. Okay, so and this particular code is reusable, so you can even edit it and you can reuse that code if you want to. Okay, so that was a sensor array analyzer app which allows you to analyze uh, sensor array of sensors or of antenna elements or microphone arrays. You can design, you can even put your own custom element, custom antennas. So, and it also generates the code. Now, let's see how we can design the antennas, and maybe if you want to check its impedance or voltage, standing wave ratio, and things like that, how can you do that? How can you um, design these antennas in MATLAB and analyze its performance in, say, a Wi-Fi band? So I'll go back to MATLAB and I'll open up a code. So the code over here is ATX sensor and a sector antenna. Now, for this particular case, we're making use of the antenna toolbox. So over here, it depends on what type of antenna do you want, and over here in this particular section, you're stating the dimensions and also some measurements. There's also, if you want to create a meander dipole antenna, there is a function for this dipole antenna. So over here, I'm setting some parameters. These variables have been previously set via width and so on. I can use this show function to see how the element looks like. If you want to have a look at the mesh structure, you can also use the mesh function if required. That's how it looks like with the mesh structure. And then if you want to analyze, check the radiation pattern at a specific frequency, um, there is a particular function called as a pattern. So pattern of the antenna at a particular frequency, 2.45. So here it's, by default, it is giving you the directivity pattern. You could also have a look at the pattern, the radiation pattern at some angles, azimuth and elevation. You can even set those, how it is looking. Okay, at azimuth of 0, 90, and so on. And if you want to have a look at the directivity performance over the Wi-Fi bands, over here what I'm doing is I'm just creating equidistant measurements of the frequency from 2.4 to 2.5 gigahertz, and I'm having a look at the pattern for those frequencies. So pattern of that particular antenna at those frequencies. So I'm just going through a for loop and soon it'll give me some kind of a plot. So that is all possible. So directivity at different frequencies, you can even, it applies these functions, apply those formulas, and then you're able to see the directivity pattern of that antenna as well. Again, a common question we had is how to do this antenna port analysis. I want to calculate the impedances. I want to calculate the voltage standing wave ratio. So typically one particular customer said getting these calculations of the impedances difficult, hard to understand what the resistance and reactance is. So now there's a function which allows you to do just that. Standing wave ratio, VSWR, is that function. You can uh, apply to that sector antenna which I've just designed. S parameters, if you want to analyze the S parameters, we now have a function for that as well. So different kinds of functionalities are now available inside these antenna system toolbox if you were to design some antennas for your own tasks. So in this particular section, we have seen is different functionalities available to design the antenna and also to analyze the performance. There's also the Sensor Array Analyzer app, which you can use to design your own custom antennas or microphone arrays. And the good thing about this app is it can also generate the code, which could be editable and could be reused. Okay, so let's go to the next part, or the last part of the agenda is how can we connect to a hardware where MATLAB can help me connect and test my communication environment on a hardware. So Now for this particular case, what we'll be doing is we'll be using USRP, which is a radio peripheral from ETIS Research, for to transmit and receive some information. So that's the setup I have got in front of me. So the laptop which you see on the left, that is connected to a USRP transmitter board. And what you see on the right is connected to a USRP receiver board. So what we're going to do is we're going to use this for transmission and reception. So I'm going to record something through my laptop, and I'm trying to transmit from the transmitter USRP thing, which is in TX. And then once that's transmitted, it gets received on this receiver USRP, and whatever corrections need to be taken, it will be done on that monitor. Okay, now before we just jump into this, let's see what different kinds of hardwares we support. Now, if you just have a look, just visit that particular link, you'll find that MATLAB, you'll get about 171 such matches related to hardware. So MATLAB can connect to so many hardwares, and it has got functionalities for you guys to play with these kinds of hardware. Different kinds of search matches you will get for different hardwares. Now, the reason, how have we helped you guys? Now, most of the times, the engineer has an hardware. It also have a computer with some software on it, MATLAB. Now, the interface, most of the times, is missing. So, interface in the sense, what kind of functionalities, or if you're playing with Simulink, are there any blocks which can help me talk to that hardware or control the hardware through the software? So we have um, helped the engineers by bringing something called as the target support packages. And where can you find these target support packages or hardware support packages? You can go to MATLAB desktop. In the home tab, can go to the add-ons, sorry, hardware support packages called, not the target support packages. So you can explore these different hardware support packages. Now, if I click on that, I'll get a window. It'll ask me how do you want the installation to be done. And once that is done, you can click next. And once that is fired up, you can see the different kinds of hardware we support. Okay. So ARM, Cortex, Apple, there are lots of functionalities if you want to use your iPhone and stream those sensor readings from your iPhone to MATLAB. That's also possible. We've got support packages for Apple iPhone, Android phones, lots of NI instruments, SDR radios, software-defined radios, and there's also USRP radio. So the USRP is a type of a software-defined radio. So that's the USRP radio package which I have downloaded and installed on my MATLAB on my machine. So what these support packages do is they give you access to the different functionalities which are not a part of the base MATLAB. Okay. So these different types of packages are available to you to explore. Okay. So, and the different kinds of SDRs are possible. If you just want to use SDR for reception, you can make use of the RTL SDR, which is a low cost, ultra low cost, about 25 US. USRP, which is what I have, is on slightly on the higher side, about 1800 bucks per board. And there's also Xilinx FPGA based radio, which is a little bit more expensive, about 2.5 grand. Okay, so let's try to design this software-defined radio in MATLAB. So what we have done, this is the typical digital communication environment. So it's a software-defined radio. So few bits will take place in the software. For instance, the initial source coding, channel coding, and digital modulation bits will happen in MATLAB. and whatever is happening later on at the receiver, that's the digital demodulation, channel decoding, source decoding, and so on, will happen in the software as well. Whatever is coming up next, whatever is remaining out of this out of this box, will happen on the hardware. That's the USRP board. So again, that's my setup. So I have got two screens in front of me. That's the laptop, which is connected to the USRP transmitter, and that's the monitor, which is connected to the USRP receiver. So let's try to see how this could be done. So what I'm going to do over here is I'm going to record my sound at the transmitter. I'm going to speak out, "We love MATLAB." That particular sound is then converted to bits. Once they're converted to bits, they're then moved on to LTE frames because we want to test the LTE system environment over here. And these LTE frames are then transmitted on those from one USRP to the other. Once it gets received on the USRP receiver, these frames are getting processed over here. The noise, if any, it will be we will be try to we'll try to reduce the noise, we'll try to reduce the channel impairments as well, decode the channel and so on. So the decoding bits happen on this monitor, the transmission bits happen on this laptop. So let's try to check this out. Okay, so that's the baseband signal waveform generation happens on the transmitter, and baseband waveform analysis happens on the receiver. Okay, so those are the steps. We'll try to record our sound, process these data bits, generate custom baseband waveform, transmit the waveform using SDR devices, capture the waveform using SDR devices, and process the received samples on the monitor. Okay, so let's see how this is done. Okay, so I'm going to MATLAB. I'm cleaning everything up. Antenna to bit simulations. I'm going to that particular folder. Oops. Okay, so now let's see the USRP in action. So over here, I'm just going to start the app. So it's called Z Run Me first. I'm just going to run it. So, and this app over here, I'm going to go for LTE standard, source type to be voice. I'm going to do it live. And the same app is actually open on the laptop. So on the laptop, I'll do the transmission, and on the monitor, I'll be doing the reception. So what I'm doing over here is the receiver, is the reception. So in order to show you what happens in the transmitter, let me open up a webcam. So I'll just fire up a webcam, and that's what my transmitter screen looks like. So over here we are just going to, it's the same app, so I can just zoom it. Oops, okay. So it's the same app, and essentially it's got the same steps. So apply parameters, generate bits, generate waveforms, set up SDR transmitter and transmit. So one by one, I will click through these steps on the transmitter side. Okay, so let's perform the first step of applying the parameters. So which means whatever setup is present over here, or whatever has been set up in the app, that gets taken into account. So I'm just taking apply parameters. And then once the parameters are applied, so I want to record something so that the bits are generated. So I'm just clicking on that and something gets thrown in my command window. So it asks us to speak. So record about 10 seconds of your voice. So whatever I'm talking now, it will get recorded. So that's getting done. It's recorded for 10 seconds now. Let's proceed to the next step. It's been recorded, the bits are generated. Now you want to generate an LTE waveform. So bits get transferred to frames, LTE frames, and soon you'll be looking into a waveform appearing over here in that particular app. Now that waveform will be the LTE waveform, which is actually ready to transmit. So it's generating the LTE waveform of your data. So it'll take a while because I'm just working with an old computer. So that's the waveform which it has generated. Now, um, that's the LTE waveform. Now we want to click through the next step. So the next step is we need to set up the SDR transmitter. So which means MATLAB finds a connection to the SDR, checks whether the board has been actually connected, and it will set up all those frequencies to transmit and so on and so forth. So if I go back, you could see that MATLAB is checking whether the software is in place. It has identified that particular board and has said the status is success, which means MATLAB has already found the board. So once it has found the board, the only step which remains is the transmission step. Now at this stage, I will go back to my screen. So I'm just going to close this video and we are going through to the receiver screen over here. So in the receiver screen, the same thing happens. Apply the parameters. So I'm going to go for LT voice live. I'm going to receive it over here. So whatever it is taken into consideration, so whatever the settings, whatever has been set over here, those variables will be created. Set up the SDR receiver. So I want to check whether the software, MATLAB can find the board, and if it does, it should come up with a success. So let's see if MATLAB can find the board. So something gets thrown in our screen. Yep, it's trying to find that board there. Okay. Okay, so it's downloading checking whether the support packages have been already been installed and so on. Okay, so again, it has identified that particular platform B200 and it has said that it is successful in finding that particular board. So that is fine. Now, once it has all identified, let's try to receive. So I'm going to hit receive over here. Um, and then I'm going to hit transmit on the other laptop. So I'm going to hit receive and then I'm going to hit transmit on the other laptop. So hopefully something will get transmitted and something will get received. All right, so hopefully let's try. Okay, so this is what it got received. So let's try one more time just in case there was any delays of me clicking these buttons. So I'm just going to try one more time. So I'm hitting receive over here and transmit on the other computer. So something gets transmitted and something gets received, hopefully in time for us to capture. Okay. Okay. Okay, so that's the signal which we have received from the transmitter. So it has finished radio acquisition. Let's try to correct those effects for time and frequency offsets. So let's see if something is getting done. Okay, so hopefully something is getting recorded. Some message will also be thrown out. Compensations have been done. Once the compensations have been done, let's try to decode the waveform. Okay, so over here, what it'll do is MATLAB will try to play with these frames, okay, and will try to decode that wave. So that's the spectrum of our voice. So it's decoding the LTE waveform of our voice. So over here, you'll see it'll process these frames. So finally, we have finished processing those frames. There were 225 such frames, which it has decoded. Now let's try to recover the source. Whether can I hear myself? I'm just trying to play.
So record about 10 seconds of your voice. So whatever I'm talking now, it will get recorded. So,
Okay, so that's what you hear. That's what you heard over here. So you could see that, right? That one was recorded at the other computer, other laptop, and we have transmitted through the USRP. It's been captured at the other USRP receiver and played on the monitor. All right, so that's an illustration of how USRP can be used with MATLAB in association with the functionalities of the LTE system toolbox. So over here, what we have done is we have made use of the LTE system toolbox, and that's the setup which I previously showed. Okay, so there are lots of other supported SDRs and RF instruments which you can mix and match. So you could have a zinc radio as the transmitter and USRP as a receiver, or USRP as a transmitter, zinc radio as a receiver, and vice versa. Ultra low cost version of the software defined radio RTL SDR is also available. It's ultra low cost, about $25 US. Different things which we have seen in this particular presentation. You can make use of MATLAB and the other toolboxes for RF systems, LTE, WLAN, antenna toolbox, phased array system toolbox, and so on to design your digital communication environment. You can also validate your models with SDR and other RF instruments and other low-cost hardware. MATLAB has got these hardware support packages which will enable you to connect the software to those hardware pieces, and also the hardware support packages comes with these extra functionalities which are available for you to use. The hardware support packages do not have any extra cost associated. They are free to use. And you can, once you have done, you can also deploy your algorithms on your target systems. Um, okay, so in this particular slide, I have added some extra resources for wireless communications. There's also training available for signal processing and communications for digital communications. So if you want to have any extra information, feel free to write to me. My email address is mandar.gujarati@mathworks.com.au. If you want to get some extra information on if you're a customer, if you're our academic customer, from universities or from one of these educational institutions, and if you want to get some more information of these trainings and resources which are available for our academic customers, feel free to write to Jonathan Coy. He's the education account manager for Australia, but he'll be happy to field any queries from other academic institutions worldwide as well. Now, with this, I hope that I have given you some information which will be fruitful for your research in wireless communications. If you have any queries, feel free to reach out to me. I'll be more than happy to answer them. Thank you very much for your time.